Welcome to the UGC EPG Pathshala lecture series in computer science. In this series of lectures, we have been looking at database management system. In this particular session, we will be continuing on data warehouse. We have started seeing with why we require this data warehouse, what are the benefits of data warehouse, then we have constructed an architecture for it. Some of the learning objectives as a continuity towards what we have seen in the previous session. We will look at what are the different views of data, how to design and build a data warehouse. These designing happens in terms of different schemas that will be presented specifically to data warehouse. We will be looking at what multidimensional data would mean, what are the different operations on data warehouse. If you look at different users have different viewpoints on a particular data. Specifically saying, we have started growing with enterprise data warehouse, which was later departmentally structured and it was individually structured. Now assume if a tourist require information on these particular organizationally structured information, they will browse for information harvested by the farmers, and the farmer, if you look at, they will harvest information from the known access paths, and the explorers will seek out the unknown and previously unsuspected rewards hiding in the detailed data. So they have different perceptions on working with these data items. So how effectively to design and build a database? Designing and building the database is a very critical part of building a successful data warehouse. This particular design is often performed by experienced database designers because it can involve taking data from multiple sources. That is what I have been mentioning it as heterogeneous sources and combining it into a single logical model. Unlike operational data sources that store data in a highly normalized fashion, the data in the data warehouse is stored in a very denormalized manner. So all the data that need not be in a normalized fashion, it can be in a denormalized fashion also, but as I have already indicated, this stores snapshot of a data wherein this need to have a very good performance. So a data warehouse often use different schema, not like one schema that has been used for operational data store where it was purely homogeneous in nature. So this data warehouse needs to accommodate different schema, like we will talk about these schemas like star schema, snowflake schema, and so to provide the fastest possible response time to complex queries. And the basis for all these aggregations are to be managed by the analytical processing tools. This OLAP indicates online analytical processing tools. So some of the components for designing a very good schema are the dimensions, the keys associated with those dimensions, and the fact and dimension tables. Let us look at all these schema design in detail. Consider any specific database organization. Towards working on a very good data warehouse, these organizations must look like a business initially. And all the data that is available with this organization must be recognizable by a business user. These data need to be approachable by the business user, and it might look as simple as it is, as it possible. So with these as basic intentions, people have started defining different types of data, different types of schema, starting with star, snowflake, and fact constellation types. As we already know, schema is to define the overall structure of a database. When we say overall structure, it includes the table name, the attributes, the keys involved along with the logics involved and the physical structured nature. So these are taken up at different levels or different types when we work with data warehouse. When we are about to talk on a dimension table, before we talk more about these dimension tables, we should make a point that all these analytical processing systems or the data warehouse systems are no more one dimensional or two dimensional. So data warehouse needs to be multidimensional in nature. I will never say that data warehouses need to be three dimensional as an extension. Data warehouses or analytical processing systems are multidimensional in nature, so that I will have several dimensions. Say for example, if I am about to sell a mobile phone in the market, then I will collect statistics on the different types of phone that is available in the market, different user groups who prefer this particular phone, and there are over a period in time, so year is calculated to be the third dimension. So for simple estimate like this, two dimensional tables are not that comfortable working with. So I have involved one more dimension as three dimensional activity, then it becomes a shape which exactly replicates a cube. So this cube will clearly indicate us with the x axis as the different phone varieties that is available in the market, different user community who uses this phone, and z represents the year wise categorization. If I consider here, I have three dimensions involved, one as phone spec, the other one as the user community, and the third one as year. So these are supposed to have individual dimensional tables. So we will talk about what these dimension tables are. These dimension tables define business in terms of already familiar to the users. So user who are already familiar with what they have known, we will collect those as dimension tables. So this will accommodate a wide row with a lot of descriptive text. And these dimension tables are small tables, about a million rows. Maximum it could accommodate about 10 lakh rows, joined to fact table by a foreign key. After I construct on this dimension tables, I might go for an advanced table which could accommodate all these dimensionality values, that is supposed to be called a fact table. But then this fact table will have the primary key of only these dimension tables. So these dimension tables are heavily been indexed, and the typical dimension tables are like time period, geographical region like market, city, the different products, customers, salesperson, etc. Some of the characteristics of these dimension tables are fewer rows than the fact tables. So these dimension tables will, as I have told you, this will accommodate only a million records, possibly hundreds to thousands or to few million. Primarily these dimensional data are character data. It involves multiple columns that are used to change dimension hierarchies. It has only one primary key as dimensional key, and those are also updatable data. Whereas I am to construct another table which is called a fact table, which is supposed to be a centralized data warehouse table. This data warehouse table will involve dimensions or the keys from all the dimension table. It will pick up all the primary keys or the key which is a point of reference with all the dimensional tables. So that will be collected and put forth on a centralized data warehouse table or a fact table. So this central table, typical example of this central table would be individual sales record, and this will store mostly raw numeric items rather than character based items. And this will have narrow rows, a few columns at most, and a large number of rows, million to billion, because it involves multiple dimensions, and it accesses via different dimensions. Like with dimension tables, these fact tables has its own characteristics. These fact tables could take up many rows from million to billion records, and it could concentrate majorly on numeric data rather than character data. It involves multiple foreign keys, whereas with dimension keys it handles only with the primary key, and all these data that is available with the fact tables are static data. 3 points that we may have to note: whenever I am to construct a centralized fact table, it is not 1 or 2 dimension that is involved. Data warehouse takes up multi-dimensional data values, and specifically these fact tables involve lot of dimension tables, and the primary keys of all these dimension tables would be considered as a foreign key in the fact table. Let us look at simple example or a type of schema, which is star schema. As we would have known from the networks concept, a star network where there will be a central hub and all the machines that are about to be connected towards the network will go through this hub. Like is the fact here, star schema also has a centralized fact table and it involves a lot of dimension tables. A single fact table and each dimension, and for each dimension one dimension table, does not capture hierarchies directly. So the fact table that I consider here will be a sales table which involves product ID, market ID, period ID, units, dollars and discount packets. If suppose I am to construct such a table called sales table, as per the records I might require a table called period table, which might again involve a lot of attributes like period ID, period description, in which quarter, in which month, in which year and which day. This will be a detailed data and this will be a current snapshot of a data. So this detailed data, I do not require all the attributes to be stored in this fact table. Instead it takes up only the period ID and stores it with the sales table. Likewise, I require information from the market, where the market has market ID, market description, the district, region, country and more amount of such information. This will be considered as one dimension and it takes up only the primary key of this table. And the third table will be of a product table, where I have product ID, product description, brand and different sizes that are available, from where I will take the product ID alone. So any specific user who wishes to query on the data warehouse, the query will initially get on to the organizationally structured, that is the fact table. Once when the data enters into the fact table, then it goes to the departmentally structured data, which will be like period data, market data and product table, and it will be individually represented back to the fact table and the fact table carries the values as desired. So this is the composition of star schema. As an extension to star schema, this star schema has not considered most of the detail or inbuilt detail about the secondary value of dimensions, whereas Snowflake represents the dimensional hierarchy directly by normalizing on these tables. Mostly we will be, as I have already mentioned, mostly we will be dealing with denormalized formats, but at times if suppose data are to be presented in a structured very understandable format, then we may have to produce all the data in a normalized way. So this will be easy to maintain and this saves a lot of storage space. So as indicated earlier, sales table has got so many list of attributes and the dimensions are available. If you look at a product table which requires product ID, not only product ID, I compare this table with the previous star schema. Not only the product ID, it requires sales supplier ID also. Then in that specific case, this supplier table need not be directly shown to the sales table. Rather, the supplier table can be shown to the product table, and the product table will in turn carry it to the fact table. So, any specific supplier who supplies a list of products is mentioned as one separate dimension, but then this becomes normalized from where I will collect all these items that will be mentioned within the product table, and from the product table it will be mentioned within the sales table. So, sales table will contain only the product ID attribute and not the supplier ID attribute, which is part of the product ID. So, this becomes the composition of a snowflake, which is supposed to be an iceberg. As an extension to it, when we go with complex applications, we may have to consider relationship between two major data warehouses or two major fact tables. So far we have been constructing only one fact table, and all the dimensions are around this fact table alone as multiple dimensions. Now that we will go for taking two different facts and sharing these dimensions which are common for these two facts. Like within a hotel, I will have booking and checkout. Booking and checkout are two different facts, but they share certain things in very common. So, I can create only dimensions, and these dimensions could be shared between these two entities. Like hotels require booking and checkout, travel agents require booking and checkout details, customer require booking and checkout details, room type requires checkout and booking details, and promotion requires booking and checkout details. So, if these are supposed to be your dimensions, then these dimensions would primarily accommodate both the facts. So, as of now we have seen three schemas, which are star schema, snowflake schema, and fact constellation schema. Now we will look at the data granularity available in data warehouse. As we have mentioned with the comparison, these data warehouses are supposed to be summarized data. So, these summarized data might reduce a storage cost to a larger volume, reduce the CPU usage because it has been structured properly, increases the performance since smaller number of records are to be accessed, design around traditional high level reporting needs, trade off with volume of data to be stored, and detailed usage of data. Solution is to have a dual level of granularity, wherein to store summary data on disk, 95% of decision support system processing done against this data, and when it is stored on tapes, only 5% of decision support system processing against the data. When we look at the levels of granularity from the operational data store, when I try to collect the account type of information, for 60 days of activity, that will be converted to monthly account register and up to 10 years, where the account will be mapped onto month transactions, withdrawal, deposits, average balance, and at the same time amount, activity date, amount, account balance will be parallelly maintained. If you are about to process on a point of sale machine, then this point of sale machine will have its ID, and every transaction will have its unique ID. So, any flaw that happens during this course of process should be easily traceable. So, this granularity gives us a clear picture of how the banking system works by collecting almost daily data and to a summarized data. And from the definition of data warehouse, we have introduced a property called integration. Integration is supposed to be collecting data sources from different sources and producing it in one specific format. Say for example, savings, loan, trust, credit card, or the different process that I wish to do, that can have same data with different name or different data with same name, data found here nowhere else available, different keys on the same data. So, what I will be trying to integrate is, I will transform all the data into one similar format. So, data transformation is the foundation for achieving single version of the truth. So, major concern for the most of the information technology concerns. Data warehouse can fail if appropriate data transformation strategy is not developed. So, any operational data source, if you consider, it will have sequential data, it will have legacy data, it will have relational data, it will have external data, but then after transforming, all the accessing and reconciling can happen. It can capture, it can condition that, it can extract, load, it can household, it can validate, it can filter, score. So, these are the different steps that happens within the transformation process, so that it becomes structured rather than saying normalized. It becomes structured so that it is very easy for the user to access in an informative manner. This is one certain example of a data transformation process. Like different formats of encoding schemes, say one application A which stores the male and female as M and F, the other application B takes the information of a male and female as 1 and 0, and application C takes the information as X and Y, and application D takes it as male and female. So, how could we effectively encode this and store it in data warehouse? It will be on singular format. So, every data source that we collect information from would be from different data sources. So, I convert all this information on a uniquely identified standard format, say M and F from this. And if we consider a unit for application A pipeline measured in centimeter, and others with a different application the same pipeline is measured in inches, something else in feet, something in yards, I will try to convert that information into say inches, which I later benchmark it. The third one is on the field, where I will have balance, current balance, balance current, whatever it could be, I mention it as balance. So, I transform into a common definition, I make this as a standard towards working on a data warehouse. So, for converting this, we will come across a lot of data integrity problems, like a same person having different spelling, Agarwal, Agrawal, Agarwal with a G inserted, right. So, this would fetch us with a lot of missing values, lot of integrity issues. So, multiple ways to denote a company's name, Persistent Systems, PSPL, Persistent Private Limited, and so, and use of different names for the cities like Mumbai, Bombay. This would ultimately confuse the user who is tending to use. Sometimes some of the records in the database would have been stored with Bombay, and now that I access with Mumbai, it does not mean that Bombay should not be recovered. Bombay also should be recovered. This transformation process looks after that. So, this was earlier said, this data warehouse or an analytical processing system deals mostly with the multidimensional data format. So, data format will be of a data cube in nature, customer, product, time. So, we tend to produce all the levels of hierarchy for these products. If you take one specific example of a cubical representation, on the X I have different measures, on the Y I have different categories, product categories, on the Z I have different years. If I pick out one specific cell, this cell gives me an information of a say sales amount for a regular product in the month of say May, sales amount for a regular product in the month of May say. So, having taken up so voluminous information, so much of data, how effectively to process on this data? With transactional processing system, we have done with lot of operators starting from select, project, join, union, intersection, Cartesian product, and so. These multidimensional data are the extension to two-dimensional data. So, anything that is existing with two-dimensional data will also exist for three-dimensional data or multidimensional data. Apart from that, having represented in different shapes, they should also have certain operators. So, the operations that are possible with this data warehouse should be roll up, roll down, slice, dice, pivot. Let me start with the slice operator. To indicate on the slice operator, just assume these values that are stored as 3-dimensional as a data bread loaf. If I am about to slice on the bread loaf, slice is a proper cut from top to bottom and in a vertical format. So when I slice it, I pick up a particular bread slice which represents for a particular, say comparing it with the previous data cube, when I slice and take out a particular detail, it should be for a particular product category because it is a vertical cut. Say with a premium gas, over different years, over different measures, I will be able to present a particular data. So that is how we represent slice. The other one would be on a dice, where I try to project on all the data. So I make a horizontal cut, I pick out that particular data, which means with the previous case, I have a time information for which I can present it. So for all product categories and all measures, I will be picking out this particular product category and I will be presenting it. So that will be your dice operator. And at times I may have to summarize on all this data, so I do a roll up. Say between Jan, February and March, I may not have multiple major of the records which are to be projected. So I summarize on all these data as one quarter, say quarter 1, quarter 2, quarter 3, quarter 4 will make it up to a year. So I summarize on all these data and say that this has been rolled up and summarized so that it becomes informative for you. At the same time, my customers might require individual data in terms of dates, so then I may have to drill down or roll down. So this is to project more of the detail. But then we have, although we have done cut on a vertical and a horizontal, but then we have not made another cross sectional cut which is to represent on the X. Instead we have another operator which is called pivot, which can change its view. So what I do is I can rotate the cube by some angle which is 90 degrees. If I rotate this cube by 90 degrees, what suddenly happens is my axis gets changed. So whatever that was previously mentioned as X, like in the previous example, measures, now these measures will become the time and the time will become the measures and the product category remains the same. So with the operator dice that I have performed already, if I do a horizontal cut again, I will be able to pick out those details which are required as measures with the operation. So apart from your normal relational algebra operators that we have been performing with like select, project, join and so, specific to this data cube we have these 5 operators like slice, dice, pivot, roll up and roll down. So as far as now we have considered about data warehouse. So if you look at the strengths of data on analytical processing systems or a data warehouse system, it is a very powerful visualization tool and it provides a very fast interactive response time. It is primarily because we have tried organizing all these data values in a very structured format, and it is good for analyzing time series data. It can be useful to find some clusters and outliers. Many vendors offer this OLAP tools. So in summary, what we have seen in this particular session, we have started with defining different schema of data warehouse, where we have started with saying star schema, snowflake schema, fact constellation schema, which are different ways of presentation for an organizationally structured data, wherein we have involved fact tables and dimension tables. Further, we have said these analytical processing systems are not 2-dimensional systems, it is more than 2 dimension, it could be 3 dimension or 4 dimension or 5th dimension. So it is multiple dimensional data stores. And finally we have talked about considering a 3-dimensional data cube. We have talked on the different operators on data warehouse like slice, dice, pivot, roll up and roll down. Thank you.